In building codes, a building is defined as a structure that stands alone and is intended for human occupancy or use. It typically has walls, a roof, and a floor, and may also have windows, doors, and other features. In the National Electrical Code, also known as the NEC, a building is defined as a structure that contains one or more enclosed spaces that are designed for human occupancy or use. This definition includes multifamily buildings, where each unit is considered an enclosed space. According to the NEC, the grounding of service disconnects for multifamily buildings should follow these guidelines. Firstly, each service disconnect must have a grounding electrode conductor, also known as a GEC, connected to the grounding electrode system. Secondly, for a multifamily building with multiple service disconnects, the GEC from each service disconnect must be bonded together at the grounding electrode system. Thirdly, the bonding jumper must be sized in accordance with Table 250.66 in the NEC. Considering a building divided into two halves, each with its own service lateral and meter stack, each half is considered an enclosed space designed for human occupancy. They can each be considered a building under the NEC definition. Therefore, the requirement to bond the GEC from each service disconnect together at the grounding electrode system applies. The size of the bonding jumper should be determined based on the size of the GEC involved, as specified in Table 250.66 of the NEC. Based on the NEC requirements, it is permitted to connect the grounds of the two service disconnects together in this situation. The bonding jumper must be sized appropriately to ensure the proper grounding of both service disconnects and the building's electrical system. The grounding electrode conductor, or GEC, is a crucial component in electrical systems, serving as the link between the system's grounded conductor, often the neutral, and the grounding electrode. Its primary role is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This ensures that in the event of a ground fault, the faulty circuit is quickly de-energized, minimizing the risk of electrical shock and fire hazards. Sizing the GEC correctly is paramount for its effectiveness. The NEC provides guidelines in Table 250.66 for determining the appropriate size of the GEC based on the size of the service entrance conductors. These guidelines take into account the ampacity of the service conductors, ensuring the GEC can handle the maximum potential fault current. Using a GEC that is too small can impede its ability to effectively clear ground faults, while using one that is significantly oversized is generally unnecessary and adds to the cost without providing a substantial increase in safety. The grounding electrode system is a network of interconnected grounding electrodes designed to provide a stable and reliable reference point for the electrical system with respect to the earth. It typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes, all bonded together to form a single, unified system. The purpose of the grounding electrode system is to dissipate fault current into the earth, providing a low impedance path for ground faults and helping to stabilize voltage during normal operation. Proper installation and maintenance of the grounding electrode system are essential for ensuring its effectiveness. Ground rods should be driven deep enough into the earth to reach stable soil conditions, and all connections between electrodes should be made using approved methods and materials to prevent corrosion and ensure good electrical conductivity. Regular inspection and testing of the grounding electrode system can help identify potential problems such as corroded connections or damaged electrodes before they compromise the safety and reliability of the electrical system. A bonding jumper is a conductor used to connect metallic parts of an electrical system to ensure electrical continuity and create a low impedance path for fault current. Bonding jumpers are commonly used to bond together metallic enclosures, raceways, equipment grounding conductors, and other conductive elements to create an equipotential plane and minimize voltage differences. This helps to reduce the risk of electrical shock and fire hazards by ensuring that all metallic parts are at the same electrical potential. Sizing bonding jumpers correctly is critical for their effectiveness. The NEC provides guidelines in Table 250.102 for determining the appropriate size of bonding jumpers based on the size of the circuit conductors. These guidelines take into account the ampacity of the circuit conductors, ensuring the bonding jumper can handle the maximum potential fault current. Using a bonding jumper that is too small can impede its ability to effectively carry fault current, while using one that is significantly oversized is generally unnecessary and adds to the cost without providing a substantial increase in safety. In the context of multifamily buildings, the NEC addresses specific requirements for grounding and bonding to ensure the safety of residents and the integrity of the electrical system. These requirements take into account the unique characteristics of multifamily buildings, such as the presence of multiple dwelling units, common areas, and shared electrical services. One key requirement is the bonding of all metallic parts of the electrical system, including enclosures, raceways, and equipment grounding conductors, to create an equipotential plane throughout the building. This helps to minimize voltage differences and reduce the risk of electrical shock, particularly in areas where residents may come into contact with grounded metal surfaces such as kitchens, bathrooms, and laundry rooms. Another important requirement is the provision of adequate grounding for each dwelling unit in the building. This typically involves the installation of a grounding electrode system such as ground rods or a concrete encased electrode, and the connection of the grounding electrode conductor to the service equipment and the building's metal water pipe if present. The grounding electrode system provides a lower impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock and fire hazards. In addition to grounding and bonding requirements, the NEC also addresses other aspects of electrical safety in multifamily buildings, such as the installation of arc fault circuit interrupters, also known as FSIs, in dwelling unit bedrooms and other areas, and the use of tamper-resistant receptacles in areas accessible to children. These requirements are designed to provide an additional layer of protection against electrical hazards and ensure the safety of residents in multifamily buildings. NEC Table 250.66 provides guidance on the sizing of grounding electrode conductors for alternating current systems. The table specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors or equivalent for parallel conductors. The table differentiates between conductors made of copper and aluminum. For example, if the service entrance conductors are 2/0 American wire gauge copper, the minimum size of the grounding electrode conductor is 4 American wire gauge copper. The table includes adjustments for different materials and installation methods. In situations where multiple service disconnects are present in a multifamily building, it's crucial to adhere to specific guidelines to ensure proper grounding and bonding. The NEC mandates that the grounding electrode conductors from each service disconnect must be connected to a common grounding electrode system. This interconnection is essential for establishing a unified grounding reference and minimizing potential differences between the various service disconnects. The NEC also requires that a bonding jumper of appropriate size be used to connect the grounding electrode conductors of the multiple service disconnects. This bonding jumper should be sized according to NEC Table 250.66, based on the size of the largest service entrance conductor or equivalent. The proper sizing of the bonding jumper ensures that it can effectively carry fault current and maintain a low impedance path for ground faults. It's important to note that the grounding electrode system itself must comply with NEC requirements, including the type and number of grounding electrodes used. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. The selection of the appropriate grounding electrode system depends on factors such as soil conditions and local regulations. The purpose of bonding the grounding electrode conductors for multiple service disconnects is to create an equipotential plane, minimizing voltage differences between the different parts of the electrical system. This helps to reduce the risk of electrical shock and fire hazards. By connecting the grounding electrode conductors together, fault current can flow freely between the different service disconnects, facilitating the operation of overcurrent protective devices and quickly clearing ground faults. In addition, the bonding jumper provides a redundant grounding path, ensuring that even if one grounding electrode conductor fails, there is still a reliable path for fault current to return to the source. This enhances the overall safety and reliability of the electrical system. The building code definition of a building focuses on its structural independence and intended use for human occupancy. It typically refers to a standalone structure with walls, a roof, and a floor, designed for people to live or work in. In contrast, the NEC definition of a building encompasses any structure containing enclosed spaces designed for human occupancy or use. This includes multifamily buildings where each unit is considered an enclosed space. Understanding these definitions is crucial for applying the correct electrical codes and standards. In the described scenario involving a multifamily building divided into two halves, each with its own service lateral and meter stack, the NEC definition of a building applies. Since each half is an enclosed space designed for human occupancy, it is considered a separate building under the NEC. Therefore, the grounding requirements for multiple buildings served by a single service must be followed. This includes bonding the grounding electrode conductors from each service disconnect together at the grounding electrode system and sizing the bonding jumper according to NEC Table 250.66. The building's electrical system relies on effective grounding and bonding for safety and reliability. Grounding provides a low impedance path for fault current to return to the source, enabling overcurrent protective devices to quickly clear ground faults and minimize the risk of electrical shock and fire hazards. Bonding ensures that all metallic parts of the electrical system are electrically connected, creating an equipotential plane and reducing voltage differences. Proper grounding and bonding are essential for protecting people and property from electrical hazards and ensuring the safe and reliable operation of the electrical system. In summary, grounding electrode conductors, or GECs, play a crucial role in providing a low impedance path for fault current to return to the source. NEC Table 250.66 provides guidance on sizing GEC based on the size of the service entrance conductors. Multiple service disconnects in multifamily buildings require bonding of GEC to a common grounding electrode system. A bonding jumper, sized according to NEC Table 250.66, connects the GEC. Building codes and NEC definitions differ, with the NEC considering each dwelling unit as a separate building for grounding purposes. Proper grounding and bonding are essential for electrical safety and reliability.